In this video, we will look at 3 examples of percentages that are reported accurately, but that can be deceptive if they are not interpreted carefully. These incorrect inferences can be avoided once you understand what the numbers actually mean. For our first example, let's take a look at some data which displays Simpsons Paradox. Now, when we consider the data in each of these different cases or pieces, we find something different than when we consider the data as a whole. Let's look first at patients with mild acne. We have 10 patients who were administered the old treatment, and 2 of them were cured. So if we're looking at the cure rate, we see here that 2 out of 10, or 20%, were cured. Under the new treatment, 30 patients were cured out of a total of 90, so the success rate here was 30 out of 90, which is 33%. For patients with severe acne, 80 total received the old treatment and 40 of them were cured, so that's a 50% success rate. And under the new treatment, 12 were cured out of 20. And that's a 60% success rate. All right, so the point to be made here is that in both cases, for mild acne or severe acne, it looks like the success rate for the old treatment was less than the success rate for the new treatment. Right? However, let's take a look at what happens if we consider all of the data at once. So we have a total of 90 patients who received the old treatment, and out of them, 42 were cured. And that's a success rate of 46.7%. And then for the new treatment, we have a total of 110 patients, right? And 42 of them were cured. So that's 42 out of 110, and that's about 38.2%. All right, so now we're seeing a different story. Now it appears that overall, the new treatment was less successful than the old treatment. So this is referred to as a paradox because neither one of these is a lie. It is correct if you're looking at all of the data to say that the new treatment has a lower success rate, and it's also correct to say that in the cases of patients with mild acne, the new treatment has a higher success rate, and the same can be said for patients with severe acne. All right, so how is this possible? Why are we seeing higher percentages in both cases, but then a lower percentage overall? Right, it might be different than what you were expecting. And I think perhaps the reason why is that when we think about combining percentages, we think, well, if it's 33% in one case and 60% in the other, then perhaps the overall percentage rate is, some sort of an average between those two. And that's correct to say. The issue is that we don't really know where that average will fall between those two groups, right? So in these cases, it really is due to the size of the groups here, right? So because we have, we've seen this before, that you can't just straight average percentages. So I can't take 33%, 60%, add them and divide by 2. That's not the right way to do it. And the reason is that we have far more people in this first group than we do in this second group. So that means that the average is going to tend to be closer to the thing with the larger group. In the same way, with the old treatment numbers, we have far more people in the second group, 80 as opposed to 10, so the average is going to lean more heavily towards that 50% than it is towards the 20%. All right, so it is possible, and now notice the percentage we're getting, 46.7, it is between 20 and 50. It's just leaning closer to 50 than it is to 20. And in the second case, the percentage is between 33 and 60. It's 38.2. It's just leaning closer to 33. So because of the relative sizes of those groups, it's possible for the averages to sort of switch like this, and overall for one to be lower when it was higher before in both cases. All right, so when you're trying to interpret results like this, you just need to be aware that there are these two cases, and that both, in a sense, are true. Neither one is a lie, but it can be deceptive if only one side of this story is told, and if you aren't aware of the other side of things. Let's look at an example with mammograms, and sort of the same idea of maybe two different stories here, but being, telling a different story depending on which one you look at. So mammograms, the claim, at least for some of the older ones, is that they are 85% accurate, right? So most people think that means that if you get your result and it comes as positive, most people think that means that there's an 85% chance that you do have cancer. Or if you get a negative result, then most people think that means that that's 85% likely. And that's actually not what that 85% means. So let's break this down into a table here with 4 components and then some totals, and then we'll see what's actually going on here. All right, so the 85% accurate, that's a commonly reported percentage, but this other one that we'll use is just an assumption for this book. So we'll assume that that cancer is present 1% of the time. All right, so let's also make the assumption that we are considering 10,000 women. All right, so roughly 1% of 10,000 women, what we're saying here is that roughly 1% of them would have cancer, and then the rest would not. All right, so that's 100 women. Okay, do have cancer, and then the other 9,900 do not. Okay, so here's where we bring in the 85% accuracy. It's actually referring to each of these categories, right, or each of these cases, right? So among the 100 women who do actually have cancer that are getting mammograms, the mammogram will detect it 85% of the time, right? Or it will detect it for 85 of those women, right? So their mammogram will come back positive, and they do have cancer. The other 15% of the time, or for the other 15 women, right, they do have cancer, but the mammogram will report that they do not. Similarly, among women who do not have cancer, right, that's what this 85% is referring to, right? The mammogram will detect it 85% of the time. Okay, so if it's 85% accurate, then that means that the women who do not have cancer would get a negative mammogram result. All right, so 85% of 9,900 is 8,415, and then the rest, 1,485, will receive an inaccurate result. They do not have cancer, but the test will show that they do. Okay, so then let's find the other totals here. So if we look at people who received a positive mammogram, right, we have a total of 1,570, and people who received a negative mammogram would be 8,430. Okay, and you can add vertically or horizontally, and we've accounted for all 10,000 women tested. Okay, so here's the question that women may actually care about, and that's what is the percentage of women with negative mammogram results who actually do have cancer? All right, so we're looking at these women here, right? They're tested, the results come back negative, and however, the test failed, and they actually do have cancer that was undetected. So that would be an important question. Right, so if we're looking at just those women, then we're looking at these false negatives. All right, so for 15 women, they do have cancer, but the test came back negative. Right, and then what's the percentage of women in that situation? Well, we need to divide that number, those 15 women, by the total, right? And here we want the total of women who had that negative mammogram result, so the 8,430. All right, so if you find the percentage there, that's 0.18%, right? Or it's roughly 0.2%, okay, or 2 in every 1,000 women. All right, so when you get a mammogram result like this, it's not that it's not that there's a 15% chance that it's wrong. It would be more accurate to say that there's only a 0.2% chance that you do have cancer when the test says you don't. The other interesting question to consider is how often does it happen that you get a positive result and you don't actually have cancer? All right, so for 1,485 women out of 1,570, the test says that they do have cancer, but they actually don't. Right, and what percent is that? Okay, well that's about 95%. All right, so even if the test comes back positive, it's actually really likely that you don't have cancer, far more than it's likely that you actually do. Okay. Another thing that's coming into play here is the fact that the rate of actually having cancer is fairly low. So the fact that it is only about 1% of the women does matter here. And you can play around with this if you could redo this table for yourself, substituting in a different percentage rate. So maybe you or someone in your family has more genetic tendencies towards cancer. So maybe you put in like 2 or 3% here, and you can go through the numbers and see what actually happens in that case. But you would just keep this 85% accurate statistic, because that refers to mammograms as a whole. All right, so when you're interpreting charts like this, it is important to know that 85% accurate among people with cancer or among people with no cancer is different than the accuracy for people who have a positive test result or people who have a negative test result. Right, so it's kind of weird here, especially when we just see this percentage and we don't really know what the context is. Okay, let's take a look at a third example. This is very similar for polygraphs or lie detectors. This works the same way as the mammograms example. So polygraphs claim to be 90% accurate. All right, so what is that referring to? Well, once again, it's a 90% accurate at detecting among people who are lying and among people who are truthful. Okay, not necessarily 90% accurate when you get a fail or a pass on this test. Okay, so let's make an assumption here, just so we have some numbers to work with. So let's say that we have 1,000 people, and let's say that 1% of them actually are lying. So you would expect this to be a fairly small number, but you can put something other than 1% in here if you would like to try it with 2 or 3 or something like that. Okay, so we have 1% of people are lying, right, or 10 people. And then the other 990 would be telling the truth. Okay, so let's put some totals here. 10 are lying, 990 are telling the truth. Okay, now out of the people who are lying, the polygraph or lie detector is 90% accurate at detecting that. All right, so 90% of 10 is 1. Oh, I'm sorry, 90% is 9. Okay, so these would be the people who fail the lie detector test and are actually lying. So the report is agreeing with what was actually going on. Okay, and then there's one person who is lying but actually passed the test. Okay, so that's the 10% of the time where the test is not accurate. And similarly for people who are truthful, right, 90% of the time the lie detector will agree with that. They are telling the truth, and they do pass the test. Okay, so they're not accused of lying. All right, so 90% of 990 is 891 people. And then the other 10% of the time, people who are telling the truth are accused of lying, they fail the test. Okay, so that's the other 99 people. Totals in this case, we have 108 people who fail the test and 892 people who pass the test. Some of whom are lying, some of whom are telling the truth. Okay, so the interesting question is, how often are people falsely accused? Okay, so the falsely accused would be people who were accused of lying, meaning they failed the test, but they were falsely accused, meaning they were telling the truth. Right, so that's these 99 people. right? And this is among people who were accused. Okay, so this is only among the people who failed the lie detector test, or the 108 people here. And as a percentage, that's 91.7%. All right, so among people who the lie detector, the polygraph claims are lying, okay, actually 92% of the time that's not true. Those people are telling the truth. And then the other interesting question is, how often do people pass the lie detector test, but they're actually lying? All right, so among people who passed the test, we've got 892 of those people. And the ones who passed but are lying, we have 1. Okay, and that's actually a really small percentage. All right, so it seems like the polygraph is when it does report that you're telling the truth, that's fairly accurate. Okay, but when it reports that you're lying, that's actually not accurate. So I think you can see why polygraphs are not allowed as evidence. All right, so when you're interpreting percentages and accuracy in situations like this, there are a few more in your textbook reading, for instance, with drug testing, or looking at numbers that are reported in politics. Just some tips to keep in mind. Be careful when combining percentages. Right, so just because you know the percentages for one category of people and for another category doesn't mean that you know what's happening when you look at the group as a whole. Okay, another thing to be aware of is what exactly a certain percentage means. So when we say something has an 85% accuracy, what does that actually mean? Is that among people who took the polygraph? Is that among people who passed or failed, and so forth? Right, and then we'll refer to probability a bit later in the course, but for now, just know that the probability of A, or something happening, is not the same as the probability of A given B. Right, so in our polygraph example, the probability that the test says somebody's lying, okay, is not the same as the probability that the test says someone's lying given that they failed the test. Okay, so we have this sort of condition, right? So the probability that they're lying or that they're truthful, right, is not the same as the probability that they are lying given that they failed the test, or the probability that they're truthful when they passed the test. If you'd like some more information about this or some other case studies, I would recommend the book that you've already read an excerpt from, How Not to Be Wrong, by Jordan Ellenberg. And there are 2 chapters in there. I believe it's chapters 9 and 10. Okay, with some other examples. He looks at a Facebook algorithm that states that, it's just a sample one, but, if somebody were to say people on this list of, this Facebook list are twice as likely to be terrorists, okay, and you can actually break that down and see how likely it is that somebody's falsely accused, or not. So it's similar to the polygraph and mammogram examples, and he has a few other interesting examples as well.